As we begin this section, let's give it a little bit of an intro. It's called Metals, Nonmetals, and Metalloids. What does that mean in English? Well, why are we doing this? You've learned maybe more than you ever wanted to about chemical reactions at this point in your life. But what a chemical change really involves is a redistribution of electrons. And that's really what we're going to talk about as we talk about the individual elements. If too much energy is required, this change will not occur. So that's really a driving force for a chemical reaction. When we were in chapters 1 through 4, you learned the language of chemistry, and I think about how far you all have come. I realize the struggles you had, and now looking back, it's not going to be as bad. You've taught yourself the mathematical manipulations. These go hand in hand. There's facts and there's methods. Both are needed to solve problems and give you insight and a job. We've talked a little bit about energy. We've talked about atom behavior, and now we're going to talk a little bit about element behavior. I refer often to LibreText. I just think it's a great resource, and that's where I took this picture of. It's a little bit different than what you'd see in your textbook, but it gets us started. So here's our periodic table. I hope you have printed one off from chapter 2 and you have drawn all over it, because now you will add even more. What are we talking about? Well, metals. Metals are on the left side of the periodic table. Yes, a student said I could do a split screen, but I got to keep this simple, okay? Metallic character increases from right to left, going in this direction, and it also increases from top to bottom. So these things way down at the bottom of the periodic table, they're the most metallic metals, all right? When I make a cation, it has a noble gas configuration, and I'll let you read the bottom because I think you're getting a good hang of this. And what I want to say is, please don't try to make a general statement about a transition metal. They are d electrons. They have multiple oxidation states. You will learn about that in 1220. But the things I've put here in bold, those are the key features that you should pick up in the chapter. If I do have a metal, it will form an ionic compound with a nonmetal. These are redox reactions. We talked about them in chapter 4. We said the metal will lose an electron and the nonmetal will gain an electron. Well, let's show another example. I have zinc, I have sulfur. Each of them has a zero oxidation state. I would be doing this demo in class. I can't do it in my dining room. I just have to tell you that it makes zinc sulfide the solid. Zinc is +2, sulfur is -2. Zinc is a metal, it lost electrons. Sulfur is a nonmetal, it gained electrons. All right, that is a redox reaction, and it is going to be a solid when we have an ionic. The second one, calcium. As a solid, it's calcium 0. Oxygen is also a 0. Calcium, has a +2 oxidation state. Oxygen has a -2 common oxidation state. So I'll be making calcium oxide, and it is a solid. The calcium, how can I do this? I'm going to do it right here. It has lost an electron. The oxygen has gained an electron. Please do not make it more complicated. Yes, BLB has some examples that are tougher. They're there to challenge you. Life is a challenge. We might as well start you going now. Now it says oxides of metal are basic. What does that mean in English? This is called a metal oxide. It has a metal with an oxygen. I'm going to write the product, and I want to tell you, you would not know this unless someone showed you. So a lot of blowback I get in this course is, how am I supposed to know something? And I'll say, well, we're doing it in lecture. So when we say they are basic, basic means OH minus, all right? So that's the whole point of this one. How about this next one? I'm going to write the product and you're going to go ballistic. It makes zinc chloride, an aqueous solution, and it makes water as a liquid. And you're going to go, I don't see any OH. Well, this is a case, and that's chemistry. Sometimes a solid will not dissolve in water. So we dropped acid. We reacted it with a strong acid. Since water was one of our products, we know that this had to act as a base. So it's not that I'm pulling the rug out from under you. I'm just starting to talk about real life chemistry, things that don't fit into little boxes with bows on them. So this section says ionic compounds They form with nonmetals, and when they do this, they are redox reactions. They form solids. The bold also says any metal oxide you have, it is going to form a basic solution. We are Gen Chem. Your homework may require you to finish an equation. I'm sorry, that's what it does. But I'm hoping on an exam they won't be quite as dastardly, okay? What about those nonmetals? Well, the nonmetals are on the right-hand side of the periodic table, and they form anions. In the beginning of this chapter, we show that anions have a high ionization energy. We show that they have a large electron affinity. You know that they form a noble gas configuration. These are the facts. So now let's give you some typical reactions for molecules. Hydrogen is a molecule, chlorine is a molecule, both of them are nonmetals. They will come to form HCl gas, where they have a shared pair of electrons. I am not talking about HCl, the aqueous strong acid. I am talking about hydrogen chloride in the gas phase. So that has also been a struggle for students. They'll say, I don't know what you're talking about, and I will agree with them. But since we had two gases as our reactants, we will form a gas product. What about the next one? We have sulfur as a solid and oxygen as a gas. What it's going to form is SO2 as a gas. All of the, sulfur's in the solid phase. Oh, I'm sorry about that, but that's essentially how this one works. And this would be when we have a coal-fired plant. The coal also has sulfur as an impurity. When you burn the coal to produce electricity, there is oxygen in the air, and what you form is SO2, and that will further oxidize to form SO3, and in the presence of water, it will form H2SO4, which is acid rain. Years ago, I had an engineer in my class who worked for AEP involved with the town of Cheshire, Ohio, where there was a blue cloud of sulfuric acid over their town. And that was from the sulfur in the coal as it burned. This could be such an interesting class, but I can't go off on tangents. I have to stick to my notes, okay? So these are going to form molecules. You'll be thrilled to learn how to do the Lewis structures of all these things in the following chapters. What else do I want to say? Well, if I have an oxide of a nonmetal, CO2 plus water, it forms carbonic acid. And you will say, how did I know that? I had to learn it. It's not something I was born knowing. But this is the famous carbonate ion. I learned that 25% of the CO2 produced goes into the water. Where did I learn that? Watching a PBS special. During the pandemic, what else is there to do, okay? So this is where we get our carbonates in the water. We also get our acids, which is making our oceans are warming, but they're also becoming more acidic, wreaking havoc on things that live in the water, okay? So that's an oxide of nonmetal. What about the second one? It is tetraphosphorus pentaoxide. When I put that into water, I form H3PO4 aqueous. Again, I would never have known that. Nor did I know that when I earned my C in Gen Chem. But that is phosphoric acid. It is in many things. Take a look at a can of pop, a can of diet of Pepsi or Coke. You will see phosphoric acid as one of the things, and phosphates. That is something that polluted the lakes probably before you were born, the Great Lakes. But what's the take-home message? Nonmetals are on the right side of the table. They're going to form anions for those two reasons: high ionization energy, large electron affinity, and they will make the noble gas configuration. They will form molecules in combination with other nonmetals, and if I have an oxide, it will produce an acidic solution. Luckily, both of these are weak acids, so they're not going to wreak as much havoc as a strong acid. On my last slide, I have the metalloids. That's that step chair. Their properties are intermediate. Their ionization energies are too high, the wrong two, to form cations. Their electron affinities are not negative enough to form anions. So they're someplace in the middle. And many of them are called semiconductors because they have conductivity in between metals and nonmetals. Now, I took this out of chapter 12 because we got to put something interesting in here. If we have very, very pure silicon, it is an electrical insulator. But when I add an impurity, it's called a dopant, what we do is we increase conductivity. And this is a field in itself. If you have me for 1220, I worked on aluminum nitride when I worked with British Petroleum. And I spent 3 years of my life trying to make aluminum nitride semiconductors. My boss was a wonderful man, and he always wondered why I would make strange analogies, but you do whatever you need to work. So these are really the key features of the metals, the nonmetals, and the metalloids. They are all facts. You could talk about them forever. You could find interesting things, but I know you want the bare minimum, so have fun learning this section.